Hello, everyone. We are happy to resume our seminars after a break. And now we start our fourth Ukraine seminar in fundamental physics. Thanks a lot for all of you for joining us. Today, we have a very interesting talk by Kai Schmitz from the University of Münster in Germany. Kai is a junior professor who chairs the particle cosmology group in Münster. And axion physics, lepton and baryogenesis, topological defects, phase transitions in the early universe, primordial perturbations, gravitational wave physics. This is an incomplete list of topics in fundamental physics, which is among the scientific interests of Kai and his research group. I have a special pleasure to introduce Kai because now I'm also a part of his research group as a Philip Schwartz Fellow and have a chance to collaborate with him and his students on different topics. But let me say a few more words about our speaker. Kai got his bachelor's degree in the Freie Universität in Berlin, and then did his master's diploma in Michigan State University in the United States. In 2012, he got a PhD in the field of elementary particle physics and theoretical cosmology under the supervision of Professor Wilfried Buchmüller in DESY, Deutsche Elektronensynchrotron. And after that, he held postdoc positions at Kavli Institute for Physics and Mathematics of the Universe in Japan, in Max Planck Institute for Nuclear Physics in Heidelberg in Germany, and at the University of Padua in Italy. After that, from 2019 to 2022, Kai was a Marie Sklodowska-Curie Action Fellow at CERN's Theoretical Physics Department in Switzerland. And finally, from 2022 until present, he has a junior professor position at the University of Münster. A couple of years ago, Kai became a member of the Nanograph Pulsar Timing Array collaboration, which is observing the gravitational waves of nanohertz range in the universe through the timing of pulsars from different pulses inside our galaxy. But this is exactly the topic of the present talk, and I think it is better to give the floor to an expert. Please, Kai, you are very welcome.
Thank you so much, Sasha, for this very kind introduction. I really appreciate it. And also, thank you very much for this great opportunity. I'm very happy to be with you here today in the fourth Ukraine seminar in fundamental physics and have a chance to talk about PTAs. You heard this already by Sasha, pulsar timing arrays, which represent galaxy-size gravitational wave detectors that allow us to search for very long wavelength gravitational waves in the nanohertz regime. And as I imagine some of you or many of you have heard, there have been some exciting announcements and some exciting developments in this field of PTA searches for nanohertz gravitational waves. Earlier this year, there have been some new announcements and new results in June, at the end of June, which mark an important milestone of the field. And I will say more about this in my talk. One particular aspect of these results that I would like to emphasize is that we can use PTA data to search for new physics. And by this, I mean new physics beyond the standard model of particle physics and also modified gravity. It's my own particular research interest. And as you already heard, I'm a member of the Nanograph collaboration, which is one of these existing PTAs. And within Nanograph, I'm actually the co-chair, one of two co-chairs, together with Andrea Mitridate from DSE Hamburg, of the New Physics Working Group. But we will come to all of this, PTAs and PTA searches for nanohertz gravitational waves and how we can use it for searches of new physics. Before we do that, let me take a step back and take a look at the current status of the field of gravitational wave astronomy. And that status is that now at the moment, the ground-based gravitational wave interferometers, in particular LIGO in the US, and KAGRA in Japan, routinely observe gravitational wave events. And these are transient events that only spend sometimes just a fraction of a second inside our detectors. And these are gravitational wave of astrophysical. Sorry. I think that we no question. I hear some voices.
Yeah, sorry. Yeah, sorry, we just have to mute some people.
Yeah, no problem. Okay,
Yeah,
so these are transient gravitational wave signals of astrophysical origin. In most cases, the mergers of binary black holes, but also mergers of binary neutron stars or mergers of black holes with neutron stars. And you can see an overview of some of these events here in this chart. So this is a catalog of gravitational wave events, including events from the first 3 observing runs of these detectors. Okay, that's the status of the field. And what is next? The next big milestone is the firm detection of a stochastic gravitational wave background. So that is not a transient event, but a background that reaches us constantly at all times and from all directions in the sky. And also a stochastic background, which basically corresponds just to random fluctuations in gravitational waves. We're not quite there yet, so we have not yet reached this magical or important, crucial milestone or threshold of a 5 sigma detection, but we're getting closer and closer to this point. And this is what these big news on June 29th were about. On that day, PTAs, Pulsar Timing Array collaborations around the globe announced their new results, and then they contain compelling evidence for the presence of a gravitational wave background, GWB, at nanohertz frequencies. So evidence means that the statistical significance is still below 5 sigma, and I will actually mention a couple of numbers later. At the moment, we have 2, 3, 4 sigma, depending on which data set you look at. But the entire field is moving into the right direction. And we can expect that now it's basically only a matter of time until, with more data and more analyses, we can reach that 5 sigma detection threshold. Now, I already said that these results were announced by different teams. Let's take a look at this work, which shows basically all the existing regional PTA collaborations. And most of them were involved in the announcements on June 29th. So we've got Nanograph, this I mentioned before, in North America, the North American Nanohertz Observatory for Gravitational Waves, of which I am a member. But then there's also the European PTA, or EPTA, which uses these 5 radio telescopes in Europe. There is the Australian PTA. It's not called the APTA, it's called the PPTA because they use the Parkes Radio Observatory in Australia, and the CPTA, the Chinese Pulsar Timing Array collaboration. And then on June 29th, the EPTA collaboration reported results together with colleagues in India from the Indian PTA. So these are all the collaborations that were involved in these announcements earlier this year. And at the same time, we've also got the MERCAT PTA collaboration, which has not yet published any results, but which is doing PTA observations in South Africa. So you see that this PTA search for nanohertz gravitational waves really is a global effort. And in particular, it is a global effort under the umbrella of what's called the IPTA, the International Pulsar Timing Array, which is sort of a collaboration of collaborations, and several of the PTAs that you can see here are members of the IPTA at the moment. All right, so let's turn to the measurement principle and think about how we can use pulsars in the Milky Way to search for nanohertz gravitational waves. And before I talk about the whole PTA, the array of pulsars, let me introduce pulsars first. So I guess as many or all of you in the audience know, pulsars are highly magnetized and fast spinning neutron stars. And they emit electromagnetic radiation. And we're typically interested in the radio radiation from their magnetic north pole and magnetic south pole. So basically there's going to be this beam of radiation along the magnetic dipole axis. Okay, and this magnetic dipole axis is typically not aligned with the axis of rotation of the pulsar. And this offset between these two axes turns pulsars into cosmic lighthouses. And we always only receive a signal, a pulse from a pulsar when this beam or this cone of radiation points into our direction, when it's aligned with our line of sight. And in this way, we then basically observe a sequence of radio pulses from these pulsating radio sources, from the pulsars in the sky. The typical rotation periods of pulsars are somewhere between milliseconds and a few seconds. And we are particularly interested in the fastest spinning pulses, those with these millisecond periods. Well, not too surprisingly, millisecond pulses. They have the largest angular momentum and represent the most stable systems. They typically form in binary systems. So such a pulsar has a companion, a second star, and the companion turns into a red giant. The pulsar can start to accrete material from its companion, and this accretion will spin up the pulsar and give it this very short rotation period. All right, so they originate from closed binary systems. And because of, well, their stable rotation and the sequence of pulses that we observe from pulses, they actually represent clocks in the sky, in particular, extremely precise, ultra precise stellar clocks that we can use for timing measurements. And that's exactly well, how we use them and their crucial aspect in PTA searches for gravitational waves. Okay, so let's now take a whole bunch of pulses and consider an array of them in our neighborhood in the Milky Way. And in this way, basically, when we look at this network of pulsars in our galactic neighborhood, we can construct a virtual galaxy-sized gravitational wave detector. So this is the sketch. This is a sketch of such a PTA, including a couple of pulsars at kiloparsec distances, maybe 1, 2, 3 kiloparsecs away from us. That means these pulsars are not really scattered across the entire Milky Way, but they are all located basically in our spiral arm of the Milky Way. And that's what I mean when I say our galactic neighborhood. Okay, and now let's imagine that a gravitational wave propagates through the Milky Way, or an entire background of gravitational waves is present here in the setup. And in these gravitational waves, they will do what gravitational waves do. They will stretch and squeeze spatial distances, and here in particular, the distances between the pulsars in the PTA and our radio telescopes on Earth that we use to record the pulses coming from the pulsars. And then if gravitational waves stretch and squeeze these distances, this will lead to tiny distortions in the pulse travel times. So if the spatial distance is a bit shorter, pulses can arrive a bit earlier. And if the distances are a bit larger, the pulses will arrive a bit later. So this will induce these distortions, changes in the pulse times of arrival, TOAs, times of arrival in our measurements. All right. And at the same time, for each pulsar, we can develop a highly precise timing model. We can take all the information that we have about the pulses and try to predict when we expect an individual pulse to arrive in the radio telescope. And then we can compare sort of with theory, with the prediction. And if we find differences, then these constitute what we call timing residuals which can contain the imprint, a fingerprint of these gravitational waves in the Milky Way. So this is sort of the measurement principle. That's how you want to use a PTA to search for nanohertz gravitational waves. However, it's not enough to do this measurement for basically each pulsar on its own, basically on a pulsar by pulsar basis, because, well, then we would not be sure that we've not just seen noise effects relevant for this particular pulsar. We really want to see a correlated effect in the time series for all the pulsars in the PTA. And therefore, to really confirm that there's a gravitational wave signal in the data, we want to go beyond such autocorrelation measurements, and we want to do a cross-correlation measurement. So that means we take the timing residuals that we can construct for each individual pulsar, and we cross-correlate these timing residuals for pairs of pulsars. And then, and this is what I will show on the next slide, there will be some characteristic pattern in this cross-correlation if the data is affected or if there is the imprint of gravitational waves in it. And if we don't see it, we can't yet claim the detection of a gravitational wave background. Okay, but let's show this in pictures. So we want to perform a cross-correlation measurement. Here on the left-hand side, you see again sort of a sketch of our PTA. Each white dot is a pulsar. And we can look at pairs of pulsars, maybe this one here and this one, which are nearly back-to-back in the sky. And then in the ideal case, if there are no systematic effects in the measurement, we would not expect any cross-correlation in the timing residuals. Everything is just noise dominated, and this is how the cross-correlation would look like as a function of the pulsar separation in the sky. Yeah, and then for these two guys here, it would be somewhere around here on this axis, a separation by, let's say, yeah, I mean, close to 180 degrees. This is the situation if gravitational waves or gravitational wave background is present in the data. And now what we see is a quadrupular pattern in the cross-correlation, this blue curve, and that is the famous Hellings and Downs curve. It has been theoretically worked out by Hellings and Downs in the early 80s, and now the curve is named after them. And this has, as I said, a quadrupular shape, which is a characteristic prediction from general relativity. Let me explain what this actually means now. So if we have two pulsars which are very close together in the sky, so a sky separation somewhere around here, then we expect a positive cross-correlation. If the timing residuals for one pulsar over there is building up, becoming larger and larger, then we expect the same effect. Then we expect to see the same effect for the pulsar next to it, right? Very close to the sky. However, if we look at two pulsars which are separated by, let's say, roughly 90 degrees in the sky, we expect a negative cross-correlation. So if one timing residual is building up, the other one is supposed to go into the other direction. And again, if the pulsars are back-to-back in the sky, the cross-correlation is expected to turn positive again. And this is a correlation pattern which is extremely, maybe even impossible, or almost impossible, to fake by other sources. We have ideas for what could give rise to a monopole correlation. A monopole correlation would just be a straight line here that does not care about the angle in the sky. And a monopole could be caused, for instance, by an error in our reference clocks. Yeah, if we get timing measurement wrong for all the pulsars in the sky, then this will be an effect on the timing residuals, but independent of the angular separation in the sky. There could be a dipole correlation coming from some uncertainty in our coordinate system. Yeah, so for these measurements, we need to know exactly where the position of the barycenter of the solar system barycenter is to, well, fix the coordinates for the timing measurements. If there's some error in the ephemerides of the solar system or in the position of the solar system barycenter, we could pick up a dipole correlation. But again, the gravitational wave background is unique because it gives us this quadruple correlation in the timing residuals. Okay, so this is the measurement principle and the theory of PTA searches. Now let's turn to the data that has been released earlier this year. So this is from all these PTA papers that appeared on June 29th. Here the main papers ordered according to the archive preprint number. In total, it was 18 PTA papers that appeared on the archive on the same day. And I think it is one of the biggest such coordinated efforts by different experimental collaborations. Yeah, and it was 18 papers on that day. I'm not sure there's ever been another day on the archive with a similar number of papers coming from a group of experimental collaborations. Anyway, let's take a look at what the different PTA collaborations report on. So these are the reconstructions of the timing residual cross correlations as a function of the angle in the sky. And these funny blobs here in blue and in green and orange over here, they're called violins, and they represent posterior probability distributions for this cross correlation here after a Bayesian analysis. So basically you have to tilt your head by 90 degrees and then basically just, cut the violin into two, and then you see a little probability distribution for the value of the cross correlation here at these different nodes, 7 different nodes on this axis in the case graph, for instance. Okay, and again, you see the theoretical prediction, the black dashed curve and the solid black curve here, the black dashed curve. All of this is, again, the Hellings's and Downs curve. So this is our theoretical prediction. And you can already see by the naked eye that this pattern starts to emerge from the data. And of course, we can make the statement more robust, but you can already see it here by the naked eye. And I can tell you that the different PTA collaborations using different numbers of pulsars, 68 for nanograph, 25 for ePTA plus Indian PTA, 32 for PPTA, and so on, that they do find evidence for the Hellings's and Downs correlations at these levels of statistical. So it's between 3 and 4 for nanograph, depending on some details in the analysis, around 3 sigma for ePTA, around 2 sigma for PPTA, and even 4.6 sigma for the Chinese PTA. But here in this case, I need to make one comment. The other collaborations perform a broadband analysis. That means they include information across all the frequencies that they have access to. In the case of CPTA, it's a narrow band analysis, and they basically look for these correlations at, well, one frequency after another. And there's basically one golden frequency, which is the one here on the left-hand side. So this is 1.5 times some reference frequency, where they suddenly get this very large significance for the Hellings's and Downs correlations. And at other frequencies that they look at, the situation is, well, not as good. Okay, so this is the outcome of the cross-correlation measurement. It really marks a big milestone in the field, because now for the very first time, the Hellings's and Downs correlations become apparent and basically start to appear in the data. We can also just look at the measurement of the auto correlation. So this is basically the way in which the gravitational wave background affects the timing residuals of all the pulsars in the PTA at different frequencies on different time scales. And again, we see some reconstruction of the results here for the different collaborations. So what you see here on this axis is the excess timing delay. This is the extra contribution to the timing residuals coming from this stretching and squeezing of spatial distances in the PTA because of the gravitational wave background in frequency space. So basically, basically extended in a discrete frequency basis. Expanded, not extended, sorry, expanded in a discrete frequency basis. And the gray violins here and the other colorful violins in the other plots correspond again to Bayesian posteriors after Bayesian analysis. And just to give you a feel for the numbers, let's take a look here at the very first violin in the nanograph data. So we can see that here the excess timing delay is of the order of 300 nanoseconds at this frequency. So this is a time scale of roughly 1/10 to 15 years. And it means that the gravitational wave background stretches and squeezes distances such that, well, over these long periods of time, 10, 15 years, the pulses from pulses in the PTA arrive 300 nanoseconds earlier or later. Now you can take that time and multiply by the speed of light, and this will give you a distance. And 300 nanoseconds corresponds to roughly 100 meters. So that means that over timescales of 10 to 15 years, the gravitational wave background will basically wobble around the position of the solar system with respect to the pulsars in the PTA, such that we get, I mean, the solar system gets 100 meters closer to one pulsar in one direction, maybe 100 meters further away from a different pulsar in the PTA. And then a couple of years later, maybe 10 years later, it's the opposite, and the gravitational waves stretch and squeeze the distances such that we're a bit closer by 100 meters to the pulsar over there and 100 meters further away from a pulsar in that direction. So this is what's happening here. And the measurements have achieved this precision, this extremely high level of precision, to detect these variations in the pulse time, or basically the position, the distances, the relative distances within the PTA over periods of 10 to 15 years, or even longer, 25 years in the case of the PTA. And that's really a major achievement and very remarkable. Okay, you can also describe this extra contribution to the timing residuals in a simpler way. Here, these violins are a free spectral reconstruction. That means that we just determine the power in this process at each individual frequency bin. We can also just by a simple power law ansatz, and these are these straight lines that you see in the different plots. This is just a two-parameter model because the power law is described by an amplitude and a spectral index. And if we do that, then we can reconstruct the parameters of that model here in these two-dimensional parameter plots. A is the amplitude of our power law, and gamma is the spectral index. Again, the results from the different PTAs. And you see they all play different games. For instance, Nanograph looks at different reference frequencies. This doesn't change the information contained in the plot. It basically, well, it's just a parameter transformation that removes some of the covariance here between the two parameters. EPTA and Indian PTA, they look at different time slices through their data, and they can do, they can respectively analyze the data for different time spans. And PPTA here in this plot looks at the variation with the ephemerides in the solar system, but you see the effect is very small. Okay, so this is the situation after the announcements in June this year. And since then, there even has been sort of a comparison analysis by the IPTA. You remember the collaboration of collaborations, the International Pulsar Timing Array. This came out a bit earlier in September. And here in these plots, I can show what I like to call the current world data on the new signal. And because it's not yet a 5 sigma detection, here I don't call it the gravitational wave background signal. I just say this, the Hennings and Downs correlated common spectrum process that is visible in the PTA data. And these plots are very similar to what you've seen before. Here on the left-hand side, it's all the violins for this Bayesian reconstruction of the excess timing delay for the different data sets. All right. And here on the right-hand side, it's these Bayesian posteriors for the practice of the power law fit. And in that paper, well, we see the posteriors that you've seen on the previous slides. But what they also do is they calculate a joint posterior for all the data together in, well, a simple way, because this is just analysis and more sophisticated analysis are, well, supposed to follow. What they do is they just take the different posterior probability densities for the different experiments, they multiply them, but they don't include any weights or any covariance or anything like this. So it's just a multiplication of all these different posteriors, and then after taking the product, you still have to properly normalize that distribution, but that gives you a joint posterior distribution here for these two parameters. And the upshot is that everything is consistent. Yeah, so there is no outlier here, and all these posterior distributions, they nicely overlap. Yeah, the 1 sigma levels, they nicely overlap. So this tells a consistent story about the properties of this new signal that is seen in the PTA data. And this is what we can do at the moment. But then if you want to have a proper combination of the data, including, well, all the right weights and then covariances, you still have to remain a bit more patient because the combination of all these data sets is ongoing at the moment and will lead to the next IPTA data set sometime in the future. And that will be the so-called IPTA Data Release 3, DR3. Maybe one more slide on this paper from September, because I am asked this question very often. People wonder, how are the pulsars distributed among the different PTAs? Is there some overlap, or are all these pulsars independent of each other? Well, this Venn diagram is the answer to that question. And what we actually see here is that at the moment, 85 pulsars are contained in the latest PTA datasets. And there's really some nice overlap among the different PTAs. So there are 10 pulsars which are observed by nanograph, and ePTA plus Indian PTA, and so on and so forth. Okay, so that's the current situation, but I mentioned IPTA DR3 already, which is scheduled to be released not next year, but maybe the year after. And this will take us into the regime of more than 100 pulsars. So this could be something around 115 pulsars, and it will include data from North America, Australia, Canada, Europe, India, and South Africa. So even more collaborations, and this will be the biggest PTA data set ever. And there's some reasonable hope that with this data set, we will be able to have a detection at the 5 sigma level. All right, so we talked about the theory and the data. Now let's turn to possible interpretations of what we see. And so for the rest of the talk, I would like to assume that what we see in the data does correspond to a gravitational wave background. I mean, we see evidence for the Hellingston Downs correlations. And yeah, so if we assume that this is really a gravitational wave background, we have to ask where does it come from? And there are two main interpretations, two main options on the table, and I will just list them here on the slide. So the first option is that the signal originates from supermassive black hole binaries, SMBs, and these are binaries of black holes with masses of the order of millions or even billions of solar masses that live at the centers of galaxies, similar to the supermassive black hole Sagittarius A star that lives at the center of the Milky Way. And the idea is that in the context of cosmological structure formation, when galaxies merge, it can happen that after galaxy merger, the new galaxy has two supermassive black holes in it, because each of the individual galaxies had a supermassive black hole at its center. Now we've got two supermassive black holes, and they fight each other and form a binary system. So supermassive black hole binaries will form after galaxy mergers, and then they will undergo some complicated evolution. But if they have a chance to get close enough to each other, to separations below 1 parsec, the evolution will be dominated by the emission of gravitational waves. And in this gravitational wave-driven regime, during that in-spiraling stage, which can last several dozens of millions of years, these systems will emit gravitational waves at characteristic frequencies, each binary system at 1 characteristic frequency. But then you take the superposition of all those gravitational waves at these different frequencies, and that superposition is a stochastic gravitational wave background. That interpretation of the data definitely is very exciting, first of all, but it's also realistic, because we know that supermassive black holes exist. Basically, most galaxies have a supermassive black hole at their center. And we also know binary systems of such objects, but still at larger separations. I mean, larger than a parsec, much larger than a parsec. So in fact, no binary merger has directly been observed as of yet. But in the community of PTA observations, there's this big hope that now the field can turn into a data-driven field. And this basically is that we can use PTA data to learn more about the evolution of such supermassive black hole binaries. So indeed, this is a viable explanation But there are also a couple of open questions regarding this explanation. First of all, the origin of these supermassive black holes and the different time involved in the problem. How long after a galaxy merger do the supermassive black hole supermassive black holes actually merge? Do they have a chance to merge within the age of the universe, or does it take much longer? How do they go down to these small separations of less than a parsec, and so on? So it's a viable explanation, but has these open questions, and all of this is a really exciting topic. We can talk more about this after the talk if interested, but in this talk, I would like to focus on the second possibility to explain the data, and this is gravitational waves from the Big Bang. And to get basically a gravitational wave echo from the Big Bang, you require new physics beyond the standard model of particle physics in the very early universe, because the standard model, well, predicts gravitational waves at some level, but nothing that would be within the sensitivity reach of PTAs. So it requires new physics, which means that this option here is much more speculative, but I think also very interesting compared to the first option. So indeed, at the moment, it is a logical possibility that the PTA signal is not of SMBHB origin. It could be new physics in the early universe completely altogether. Or it may be that what we see is basically the combination of two signals, so that the signal receives several contributions. It's an astrophysical signal from supermassive black hole binaries, plus on top a gravitational wave signal from the early universe. And if we take that interpretation seriously, it opens up a completely new window onto early universe cosmology and particle physics, because now we can use the PTA data to probe and constrain cosmology at very early times and particle physics at very high energies. And I would like to emphasize the probe and constrain here. By probe, I mean that we can suppose that one early universe model is the correct description and origin of the PTA signal, and then we can just fit it to our data and see what are the best fit points in parameter space. But even if we don't believe in that and think, no, it's a physical interpretation, it must be supermassive black hole binaries, even then, we can take the PTA data and constrain those scenarios of the early universe. We can take our models that we're interested in and identify the regions in parameter space where the gravitational wave signal would be way too large. Yeah, we can go to a region of parameter space and say, here at this parameter point, gravitational wave signal should have been detected by PTAs a long time ago, but it hasn't. So we can declare this part of parameter space ruled out, excluded. So in this sense, irrespectively of the origin of the signal, we can take PTA data and constrain models of new physics in ways in which it's not possible to do this in other ways, with other methods. All right, so for the rest of the talk, I would like to focus now on this second possibility and talk about how we can use data to probe new physics, to probe new physics at the PTA frontier. And I would really like to emphasize that this opens up a new frontier in particle physics. I like to call it the PTA frontier. We can probe regions in parameter space that are inaccessible methods. We can derive new constraints irrespective of the origin of the signal. This is what I just said. And all of this is complementary to efforts at other frontiers of particle physics. So we can compare this to the energy frontier, where we construct, for instance, particle accelerators at ever larger and larger energies to probe sort of the subatomic world at ever shorter and shorter distances and try to find elementary particles or new particles at higher and higher masses. Well, there's the energy frontier. Then there's the intensity frontier, which works with very intense particle sources and that looks for very rare events. For instance, Kamiokande and Super Kamiokande were initially intended to search for and find proton decay, a very rare process predicted in grand unification, and so on and so forth. So we've got these other frontiers, the energy frontier, the intensity frontier, but now the PTA frontier opens up another window onto new physics, which we can use to probe models for which would have no chance to find them or to probe them here in these experiments. I would also like to take 1 minute to give a shout out to our team that was involved in our nanograph work during the last year. All right, so we've got many members of my group here in Münster, and then also Andrea Mitridata, who has been the co-lead together with me at DZ Hamburg, and more people in the US. This has been a core team, but we had more people on the team as well. So Adila, for instance, who's in the call, I feel bad that your picture is not here on this slide. You contributed to this paper. And what we did was to take the new physics, to take the nanograph 15-year data and to search for signals from new physics in it. And this led to this paper here on the archive. And to carry out these searches, we had to develop new software tools. That's what we did. And this led to our code, PT Arcade, which is now publicly available. And you can also use it if you want to fit your own favorite BSM model to PTA data. All right. So yeah, this is it. Just a brief shout out. It's the code developed for our nanograph paper, and you can find it on GitHub. And we also have a documentation on the archive. Okay, so let me just give you a brief overview of the results that we find, but then I want to turn to more concrete models and talk about them in more detail. What we do in the paper is to carry out a comprehensive Bayesian model comparison. And I don't want to talk too much here on this slide. I just would like to tell you what we do in broad terms. So we take a new physics model, for instance, gravitational waves from inflation. This is the very first one here, and compare its capacity to fit the new physics, its capacity to fit the nanograph data to the capacity of a reference model to fit the nanograph data. And this reference model is supermassive black hole binaries only. And then the ratio of the two marginalized likelihoods defines the base factor. So if the base factor is larger than 1, it means that the new physics model gives a better fit. And if it's smaller than 1, it means the supermassive black hole binaries give a better fit. And then we repeat this analysis for all the new physics models that you can see here. I will say more about them in a minute. We repeat the analysis for the new physics models, but we combine them with a second contribution to the signal, a signal from supermassive black hole binaries. So this is now sort of a hybrid model where we say the signal receives 2 contributions from new physics and supermassive black hole binaries, and we take that hybrid model and compare it to our baseline reference model. And this gives us the red points here in this plot. So the upshot of this analysis is that many new physics models give us base factors of order 10 or even 100. And at face value, you would say, oh, that's great. I mean, we've got many new physics options that can explain the data better than the supermassive black hole binaries. But we have to be extremely cautious and careful about conclusions. What we see here is interesting, but it's not conclusive. And the reason for this is that basically all the ingredients that go into this analysis here suffer from big uncertainties. This affects the description of the supermassive black hole binaries, but also lots of uncertainties in the description of this from new physics. And before, we make some significant progress to remove these uncertainties, we should be very careful about these base factors and not jump to any premature conclusions. So what we can say is that many models can fit the data. That's very interesting. And they remain viable options on the table, but the situation overall is inconclusive. I mean, one thing we can say maybe is that stable cosmic strings, which you can see here, stable cosmic strings are these 4 points. They don't do such a good job. Here, the supermassive black hole binaries give the better fit, but then for everything else, we just don't know at the moment. All right. This is how the violence that you've seen before looked like with gravitational wave spectra superimposed from new physics scenarios. So we've got gravitational wave spectra from inflationary gravitational waves, phase transition, scale-induced gravitational waves, and so on. I would just like to point out that these gravitational wave spectra, well, they look all rather similar, but this is by construction, because all of these gravitational wave spectra are supposed to fit the same data. So they all lead to a good fit, and they all look similar by construction, because they're supposed to go, or they're supposed to be close to all of these violence here. And so that's not such a big surprise. The more relevant question is, okay, if this is the type of gravitational wave spectrum that we need to explain the data, how do I actually get it coming from the new physics models? So which parameter values actually do predict a gravitational wave spectrum of the right form? And this is basically the question at the heart of our Bayesian inference problem. So now I would like to fit new physics models and learn more about the parameter space of these models. And yes, so I think in the remaining time, still have 10 minutes or 12 minutes because we started a bit later. I would like to just highlight a few example scenarios. I will not show all of them that I have here on the slides, but you can take a look at the slides later, or we can even chat after the talk. Let me start with one scenario, one beyond the standard model scenario that can give rise to a gravitational wave spectrum. That's cosmic inflation. And here on these slides, I would just like to start with the big basic questions, the big questions that motivate us to consider these scenarios in the first place. So in the case of inflation, the big questions are, what set the initial conditions of the hot Big Bang? Why do we observe that our universe is homogeneous, isotropic, and spatially flat on cosmological scales? And on top of this homogeneous isotropic background, we observe fluctuations in the universe. We see temperature fluctuations in the cosmic microwave background. And again, the question is, where do those fluctuations come from on top of the homogeneous background? And in the standard model of the contemporary standard model of cosmology, the answer to these questions is cosmic inflation, a stage of exponentially fast expansion before the hot Big Bang, which basically sets up the right initial conditions for the subsequent hot Big Bang phase of radiation-dominated expansion. Inflation requires a form of dark energy to drive this exponentially fast expansion. And typically this can be provided in form of the potential energy of a scalar field, some inflaton field, which drives the inflation. Now we've got this physical system. We can describe it in the language of quantum field theory. Then fluctuations in all the dynamical quantities, fluctuations in the inflaton field and fluctuations in the metric, and maybe even other degrees of freedom that are around, will be produced and stretched to superhorizon scales and all of this. And eventually, these fluctuations coming from inflation define or represent the initial conditions for scalar and tensor perturbations in the early universe. And this is what we call the primordial scalar and tensor perturbations. The tensor perturbations, or the scalar perturbations, turn into or seed the temperature fluctuations in the CMB eventually, and the tensor perturbations correspond to gravitational waves coming from inflation. So this is how gravitational waves are produced during cosmic inflation. And we can test this hypothesis with the PTA data. So here I would like to emphasize would like to answer the question, what can we learn from the PTA data already at this stage, given the data from earlier this year? And we work with a simple parametrization of our gravitational wave spectrum from inflation. The basic input quantity is the primordial tensor spectrum. We don't assume any microscopic model, but just parameterize it in terms of a tensor to scalar ratio and some spectral index. Then we also include some transfer function for everything that happens after inflation. This is why the reading temperature enters into the description of the gravitational wave spectrum. And now we have a nice 3-parameter model that we can fit to the nanograph 15-year data. And then here in this plot, you see the Bayesian posterior constraints on this 3-parameter model. I don't want to spend too much time with the details here. I would like to emphasize the lessons that we can learn from this fit already at this point. So we see that in order to explain the PTA signal, we need to have a strongly blue-tilted spectrum index between 2 and 4. This is not easy to achieve in simple models of inflation. So this inflation interpretation of PTA data already assumes some non-minimal dynamics during inflation, maybe, for instance, involving more degrees of freedom and things like particle production and inflation that can give rise to such a steeply tilted gravitational wave spectrum. See that reheating at a scale of 1 GeV can lead to a noticeable feature in the gravitational wave spectrum. This is also reflected in these posteriors. So what this means is that, if with future data we should narrow in on some parts here of this parameter space, we may be able to use PTA data to measure the reheating temperature or to probe the dynamics and the physics of reheating. That's very interesting. And in other parts of the parameter space, if we extrapolate the gravitational signal to higher frequencies, we find that the integrated energy in gravitational waves will contribute to dark radiation and actually give us too large a contribution to dark radiation. This is labeled here by N effective, the effective number of neutrino species, which allows us to rule out this part of parameter space. But again, depending on where we end up, maybe here eventually in this parameter space, there might be some interesting interplay here. And it may even be that we can test some of these predictions here with measurements of N effective or with these searches for dark radiation. All right, so I think I still have something like 7 minutes or so. That's perfect, because then I can turn to another scenario here. I want to skip the primordial black holes. We can talk about this later if you want. I want to emphasize this scenario here, which are cosmological phase transitions. So the big questions that motivate us to look into the scenario are the following. We know about the Higgs mechanism in the standard model and the quark-hadron transition in the standard model. But we would also like to know how these transitions are realized in the early universe. And apart from this, we can also speculate about physics in dark sectors. Maybe there are dark sectors, new fundamental forces, maybe some dark Higgs mechanism that is also realized, that exists beyond the standard model, and that corresponds to dynamical transitions in the early universe. And whenever something like this happens, we encounter a cosmological phase transition in the early universe. These are changes in the vacuum structure of the quantum field theory, and they correspond to the electroweak phase transition in the standard model, and the phase transition in quantum chromodynamics, the QCD phase transition. However, in the standard model, the standard model predicts these two transitions to be smooth crossovers. That's interesting, but it's bad news for the production of gravitational waves. Gravitational waves can be produced in a cosmological phase transition if it is of first order. We don't have that in the standard model. There's no first order phase transition. So to get a strong first order phase transition, we need to have physics beyond the standard model, new physics again. And so basically this phase transition interpretation of the PTA data provides another window onto new physics. And we can probe scenarios of new physics, BSM scenarios, that either include a completely new cosmological phase transition of first order, or BSM scenarios that turn one of these here, and in particular the QCD phase transition, into a phase transition of first order. Once we have a first order phase transition, we will produce gravitational waves from collisions, sound waves, and turbulence in the plasma. So let's ask again the question, what can we learn from PTAs for this interpretation? Again, we have a simple parameterization of the gravitational wave spectrum in terms of a peak amplitude and a peak frequency. Here we can parameterize the model for gravitational waves from bubble collisions in terms of 3 parameters. T is the temperature scale of the phase transition, the so-called percolation temperature. Alpha is the strength of the transition. basically the latent heat released during the phase transition. And R star is the separation of those vacuum bubbles at the time of percolation in units of the Hubble radius. Okay, and here we see again the Bayesian posteriors for these model parameters. Again, let's not focus too much on these. I would rather like to focus on the lessons that we can learn from our analysis. So we see that the PTA data prefers strong transitions, where alpha is 1, and this is a large value. Slow transitions, where those bubbles or the bubble separations are as large as the Hubble radius, and transitions at temperatures of the order of 100 MeV. And this number here, 100 MeV, I think is the most interesting one, because this is just in the right ballpark for BSM modifications of the QCD phase transition. So I think now it would be very relevant and worthwhile to go back, look at the QCD phase transition, and see what BSM modifications can turn it into a first-order phase transition, so that we do get this strong first-order phase transition at temperatures of around 100 MeV. If it's not the QCD phase transition, and I mean, we want to stick to this phase transition interpretation, another possibility is a phase transition in a dark sector, which involves completely new degrees of freedom. But then that interpretation would be complementary to laboratory searches for these new degrees of freedoms. All right, so again, here in this case, we can learn a lot about such scenarios already from the present data. I will skip this scenario here, and yes, would like to make one brief comment. So far, I only talked about new physics in the early universe and how it can lead to a stochastic gravitational wave background. There's another a whole other class of new physics signals that we can also probe with the PTA data, and these are deterministic signals. And I don't have the time to go into any details here. I would just like to mention it on one slide. So now we can basically go from very high energies in the early universe back to the present day and look at possible effects of new physics right here today at home in front of our doorstep in the Milky Way. And what can happen here is that different types of dark matter, for instance, ultra-light dark matter or dark matter substructures, for instance, in the form of primordial black holes, they can induce these deterministic signals. So, I mean, there are a couple of different effects that you can look at. One, for instance, is metric fluctuations coming from some oscillating ultra-light dark matter field. You can imagine that if this ultra-light dark matter field is oscillating in the Milky Way at the position of the pulsars, at the position of the Earth, it will disturb the gravitational background, and the pulses coming from the pulses have to travel through this gravitational wave background. And then these metric fluctuations can then give an imprint in a deterministic one on the timing residuals. So we can use these signals just to search for new physics and dark matter, in particular in our Milky Way. At the moment, we find no signals, which means we can put lots of bounds. And in some cases, these bounds on parameter space are exceeding constraints from terrestrial experiments. So these are, for instance, constraints on some U1 model, where a new vector boson couples to couples to barrier number or B minus inside the pulsars and the Earth. All right, so these are different types of new physics that we can probe with PTA data. I looked at what happens in the early universe and one slide for new physics effects today in the Milky Way. And the last 3 minutes, I would like to address the question of how we can make progress in the future and maybe trying to tackle different possibilities for the origin of the signal. And there are two main complementary observables for this. And the first one is anisotropies. So in the future, it's going to be extremely important to look for anisotropies in the gravitational wave background in the sky. And here you see a simulated signal for anisotropies for the astrophysics interpretation, so for supermassive black hole binaries. And that just means that if there are supermassive black hole binaries somewhere in distant galaxies in certain positions in the sky, they can lead to these fluctuations in the gravitational wave background amplitude. So basically, because of the discrete source population, we've got these fluctuations here, and that can be predicted, and we can search for it with PTA data. And I showed a picture like this because it, of course, reminds me of this baby picture of the early universe, the temperature fluctuations in the CMB. So I like to think of all of these developments in the following way. We can think of the GWB as the 21st century equivalent of the 20th century discovery of the CMB. And of course, there's the big hope in the community that now we can repeat many of the analyses for the GWB that we previously carried out for the CMB. All right, so with nanograph, we can look for anisotropies in the sky, in the gravitational wave sky. And on the right-hand side here, you see some constraints coming out of this analysis. We can basically decompose the gravitational wave signal into some multiple bases and then constrain the coefficients of these multiple terms. At the moment, we only have upper limits, but then these colored bands here correspond to theoretical expectations for supermassive black hole binary populations. And you see the current sensitivity is already at the level of these expected anisotropies. And well, we have not excluded yet the entire parameter space, but we cut into the relevant parameter space already now, but still we don't detect a signal. And that's interesting. All we can do is to put upper limits on the deviation from a monopole as a position here and as a, independence of the position in the sky. And you can ask that question and wonder if we have not yet seen any anisotropies in the sky, and this will persist with future data, can we take this as a hint of a primordial origin of the signal? And certainly at some point, we'll have to take that very seriously. If the anisotropies just don't show up and the signal remains smooth across the entire sky, no matter what we do, this would then really point to a primordial origin of the signal. All right, so I still have maybe 1 minute and then I'm done. The second complementary observable is we can look for continuous wave signals. So these are just signals from individual binary systems. Yeah, so if there's two supermassive black hole binaries in one galaxy over there, that could result in a continuous wave, gravitational wave signal coming towards us. If we look at the data, first we find interesting in the data, but all of these hints disappear after further scrutiny. So overall, we detect no signal. And again, we can just put upper limits as a function of the position in the sky. And so the prospect is that in the future, we can combine everything. We can combine the information on the spectrum. We can take into account the information on the anisotropies, information about continuous wave signals. We can even combine this with other searches for gravitational waves and complementary observables like CMB observations, searches for spectral distortions and things like this. If we take everything together, this wealth of information, hopefully, and I think there are good reasons to believe that this is going to happen, we can identify the origin of the PTA signal. So these are exciting times, but it's only the beginning. I'm particularly interested in new physics at the PTA frontier. This is a rich and exciting research program for many years and decades to come. The plan in our research group, in my research group, is to continue building new models. We need to improve the theoretical modeling of existing scenarios, existing models, and we want to develop better analysis software tools. And then we have to streamline our analysis pipelines and get ready for the analysis of the next round of PTA data sets, the IPTA DR3 and beyond. So stay tuned, and thank you very much for your attention.
Yeah, thank you very much for a wonderful talk. Now we go to the questions and answer sessions. So, dear colleagues, if you have some questions, please just unmute yourself and ask the question.
Hello, can I ask a question?
Yeah, sure, please go on.
Yes, sure, please.
Okay, thank you. Thank you for your presentation. Can you estimate how much time would be needed to have this distinguishing between possible source of signal with current technologies?
Yes, that's a very good question. I think this is maybe the most important question in the entire field. So thank you very much for asking it. I mean, it depends. It depends on what we actually discover or find in the future. I mean, it will not take, much longer anymore. I mean, a long time to improve these searches for anisotropies. So there will definitely be progress for these searches in the coming years. So we're talking about things happening within the next 5 years, maybe let's say in this decade until 2030. In that time frame, we will definitely make some significant progress in the search for anisotropies and also in the search for continuous wave signals. At the same time, we'll also have more information on the spectrum. And then it depends on what we find. If in 5 years, we see some very clear sign of anisotropies, and it is very nicely consistent with expectations from supermassive black hole binaries, then within that time frame, within the next couple of years, I think we'll have more supporting evidence for the astrophysical interpretation, the supermassive black hole binaries. The same also for the continuous wave signals here. On the other hand, if nothing like this should show up, so we don't detect any individual binary, we don't detect any anisotropies, well, then this will be a measurement, at least for these observables here. At that point, we can't yet really clearly say what the true origin of the signal is. It will give, more credence to the possibility that the signal comes from the early universe. But still then, within the next 5-10 years, we will collect information on the spectrum. Let's go back to this plot here. We'll go down to lower frequencies. Also, the uncertainties can be reduced. So also within the next couple of years, let's say 5 years, we'll have much better information on the spectrum and can say, maybe more about which models give us a very good fit and which models don't give us such a good fit. This will not yet be conclusive at this stage. So for this reason, it's important to look at even more observables. There will be other gravitational waves. So in some cases, these signals go to much higher frequencies. For instance, in the case of stable strings, metastable cosmic strings, and all of this, then if there's a detection of a signal that's consistent with what we see here for PTAs in the frequency parts of the spectrum, maybe with even LIGO, or then in the future Cosmic Explorer, Einstein Telescope, and LISA. This can provide more circumstantial evidence for one of these interpretations here. Or you get more information from other probes, CMB, spectral distortions, and so on and so forth. So yes, it's hard to make a prediction now at this moment, but progress could be very fast in principle. So we don't have to wait for years. I think within the next 5-10 years, we'll make some significant progress in the field. And then it depends a bit on what we find. If it's really one of these cosmological possibilities here, we may have to wait a bit longer, put this together with other observations. But then still, there are good chances that with new gravitational wave observatories like LISA in the next decade, we will know much, much more about this at the end of this decade, or at some point in the next decade, at some point in the 2030s. Yeah. So I think it's exciting times, and there's definitely some good progress ahead.
Thank you. It's fascinating. Thank you.
Yeah. Sorry for such a long answer. I was talking again for 5 minutes, but yeah.
No, it's great. Great.
Yeah.
Okay. Who else has the question, please?
I want to ask about the slide number 8. Please show the slide, and please
Yes.
look on the lower right picture. No, previous one, please, and then number 6. No, previous one.
This one?
Yes. If we look of this, I interested in CPTA data. If we look the characteristic curve, we have the minimum at the perpendicular direction, and we have a maximum from the same direction for two quasars and for the opposite direction. It is rather obvious. But if we look on this, we see that the right edge is not so optimistic at this. But we look at this, we have more pulsars, 68 against 57. We have more years of observational. But here we have the difference on the level on 3 or 4 sigma, and here we have 4.6 sigma. And for me, this is very strange situation. Can you have some comments about this? Because the right edge is very, very strange.
Yes, yeah, thank you very much for your question. I think, again, it's an excellent question. And to be honest, I would also like to better understand what's happening here. I mean, of course, I know what's happening in the analysis of the nanograph data, and I know exactly how we obtain this level of statistical significance. I've got some backups, like some p-value tests for some test statistics. The test statistics are some base factors or something that we call some optimal statistic. And this is how we quantify our significance for ups and downs correlations. And I think this is some robust statement here, in particular, if we just state which depends on some details in the analysis. In the CPTA case, there's really not much I can say. The data is not publicly available. And in the paper that has come out so far, they don't share too many details. So it's a bit difficult for people from the outside to reproduce analysis and their results. And if I say difficult, I should also say, I mean, what I mean is impossible. We cannot reproduce the results at the moment. If you look at the paper and you read it, then, well, you will see that the analysis is a bit different from what we do here. Again, I said it before, this is a narrow band. They have 4.6 sigma for the entire data set. Basically, they just take data for individual frequencies. Maybe they just go here to this frequency or to this, different frequencies, and try to reconstruct the cross correlation at these different frequencies. And then they find different values. Then they find evidence for the ups and downs correlation at different levels of statistical significance. So it's at that point, it's basically a statement in the paper. You can also say it's a claim, but I think it's very difficult for somebody from the outside to cross-check these statements. This is the current situation, and maybe it will change in the future. So I don't know, but what I understand is that this first CPTA paper, which came out in June, was just the very first one. It's supposed to be sort of a teaser, some announcement, or some first volume of some more comprehensive results, which are going to be published in the future. So my understanding is that CPTA will have many more publications in the future, not just one, but I think it's going to be a larger number, 5, 6, 7 papers. I think they have not yet come out. Please correct me if they have come out, but I think they have not yet appeared. They will appear in the future, and hopefully with this much more comprehensive information, 5, 6, 7 papers, it will be possible to see what they actually did and also reconstruct and repeat parts of the analysis. At the moment, it's not possible. And all we have basically are, these statements and these numbers from the paper in June. That's the situation. And apart from this, I basically have the same questions as you.
Thanks.
Okay, thank you very much. Please, colleagues, who else has the question? Please just unmute yourself and ask. Okay, then maybe I have one regarding the constraints on inflation. As far as I understand, the modes which are relevant for nanohertz gravitational waves, which are observed now, they cross the horizon during inflation, not at the same time as CMB modes, and much closer to the end of inflation. So in principle, if the spectrum is not just a power law and it has more complicated form, this means that this value of R and this value of NT that you are presenting here, these are not the same values of R and NT that we are usually see in the literature, for example, from Planck collaboration and so on. Does this mean that maybe still some conventional inflationary model can be still viable, but only maybe close to the end of inflation, they have some strong features that maybe modify the gravitational wave spectrum? What do you think?
Yes, thank you very much. That's an excellent question. Yes, so I mean, in a sense, to fit the PTA data, we only need sort of a local parametrization of the gravitational wave signal. And if we write down such a power law like here, well, you can use it to parameterize the signal in the PTA. But for that model, it's not necessary that you can basically extrapolate all the way down to CMB frequencies. Still, if NT is just a constant over many orders of magnitude, then in that case, there's this identification here, and we can say, okay, this power spectrum here is defined at the CMB scale. I put the frequency FCMB here, and these are the same parameters. So what I mean is you can extrapolate to the CMB, but then you have to assume a constant spectral index, but you don't have to. You don't have to extrapolate. You just need the spectrum in the PTA band. And then to answer your question, or the second part of your question, I think it's difficult. And I mean, if to be able to construct such a model based on standard ingredients that only at the variant of inflation, then I think we should write a paper on it, because that would be a very option. I mean, as you know, the simplest models of inflation, we just have single field slow roll inflation, have to satisfy consistency relations among the inflationary observables. In particular, for single field slow roll inflation, there's some relation between the tensor index to scalar ratio, even with a negative sign. So NT has to be -1/8. I think that's it. Times the tensor to scalar ratio. Yes, and this would not even the spectrum. This would give you a red tilted spectrum. And then in combination with the red tilt and the scalar power spectrum, you would conclude that the simplest models of inflation, if decreasing power, smaller power in tensor perturbations if you go to larger frequencies and PTA scales. So I think these simplest models that obey these consistency relations, it will just not work. And then the question is, how do you get around it? And I mean, we do have constraints on the 10 to scalar ratio at CMB scales. Yeah, upper limit on R of the order of 0.04 or 0.36 or something like this at the CMB scales. If that's into omega gravitational waves, have the strength of the gravitational wave spectrum, you basically assume some flat spectrum all the way to the PTA scales. You would get a prediction of the order of 10 to the minus 16. Yeah, I can show the plot again. So with a bound on the tensor to scalar ratio and no strong scale dependence, we would be down here at 10 to the minus 16. Scalar is at 10 to the minus 9, roughly, or 10 to the minus 10, 10 to the minus 9, and then, okay, somewhere here. Okay, these are many orders of magnitude, yeah, say 7 orders of magnitude. And yeah, I think you have to work hard in simple models. I mean, simple models to get this enhancement by 7 orders of magnitude. I think that even, yeah, constraints from things like the null energy condition and things like this. And if you want to preserve all of these conditions, then it's impossible to go up by 7 orders of magnitude. And then you have to at least go beyond single field slow roll inflation and consider some type of non-minimality. But this can mean many things, right? I mean, non-minimal can be maybe just one small extra ingredient. There are papers that consider some sources of null energy condition violation during inflation. They can also produce a very strong signal at large or at PTA frequencies. And of course, you know that particle production during inflation can also boost the gravitational wave signal. So this is, of course, what we are mostly interested in, that you take models of axion inflation, for instance, where you have a new source term on top of vacuum fluctuations. Yeah, but I think just a tensor vacuum fluctuations in the simplest models, especially if they satisfy these consistency relations, and you don't want to violate the null energy condition, it's, I would say, more or less impossible to go up here by 7, 8 orders of magnitude.
Okay, I see. Thank you very much.
Yeah. But
okay.
Yeah, I think, I mean, if you maybe just one last statement.
Yeah,
sorry.
sure.
I think if you make statements like this, and also because this is going to be recorded for YouTube, if you make statements like this, I think there are always people trying to find some loopholes in these statements, right? And you really have to, you have to be very careful about your assumptions that you make when you construct inflationary models. So in some sense, I think it's an open and interesting question to see which models of inflation are actually possible, are actually able to give us such a strongly enhanced signal at these frequencies. I think, for me personally, the most attractive candidate is particle production during inflation. But that's not the end of the story, and there are more proposals in the literature. So I think it's an interesting question and also a field of active research. Mm-hmm. That's it. Sorry. Yeah.
Okay. Thank you very much. Okay. So, dear colleagues, do we have more questions to our speaker? I guess not. Right. Okay, then let's thank Kai again. Thank you very much for a wonderful talk. And thank to all of you for participation. Yep. Okay, then have a nice day and goodbye.